Okay, so up until yesterday, we've been modeling the motion of objects with constant velocity. Today, we're going to be modeling the motion of objects that are accelerating, right? Kind of like the toy car in the toy car lab. Accelerating means that the velocity of these objects will be changing, right? So just like the toy car in the toy car lab yesterday, the velocity is going to be either increasing or decreasing um, in all of the examples that we're going to be working with for the rest of the unit. So objects will accelerate or change velocity when they have a force or a net force acting upon them. So we're going to talk more about forces in our next unit. That's going to be what we're focusing on. And then stronger forces will cause objects to change velocity faster. So if we want to think about the toy car lab from yesterday, gravity was that force. Right? The force of gravity would be stronger if we had a steeper ramp, right? And that would make the car accelerate faster. Okay, so let's kind of go over the variables for today's lesson. First up is time. We've been talking about time. Time has the symbol T and it has units seconds. Next up is our next variable is going to be change in velocity. So we've been talking about velocity. We're going to talk about change in velocity today. And so the symbol, the V is for velocity like we've been using. And then this triangle represents change. That's the Greek letter delta. And physicists use delta in their formulas when they want to represent that something is changing. So because acceleration causes changes in velocity, we're going to be studying those changes in velocity today. And then the units are meters per second for velocity. All right, and then our last variable is acceleration. Acceleration has the symbol A. That's probably not a surprise. The units are meters per second squared. And so this squared is a superscript. Sometimes it's also written like this, meters per second per second. You'll just kind of see me write it both ways in today's lesson. Okay, so we're going to be dealing with this acceleration triangle today. And so we can see delta V goes on the top, and then A and T go on the bottom. And so when we cover up delta V, we get delta V equals A times T because those two are at bottom. When we cover up A, we get A equals delta V over delta T, or delta V divided by delta T. And then when we cover up T, we get T equals delta V divided by A. Okay, so then let's go through some examples. Oh, sorry, one more page of notes. The easiest way to determine how much the velocity of an object has changed is to subtract the velocity from the start of the object's motion from the velocity at the end of the object's motion. So let's kind of write this out a little bit more simply. Change in velocity equals final velocity minus initial velocity. Or if we're going to write that as an equation, delta V equals V final minus V initial. Write down this equation. We're going to be using that today. In fact, if you want to, you can add it to your acceleration triangle so that you've got all your equations in one place. Okay? All right, so now let's go through our first example. A roller coaster has a speed of 10 meters per second at the top of the hill and 25 meters per second at the bottom of the hill. If the roller coaster reaches the bottom of the hill in 3 seconds, how fast is it accelerating? Okay, so first we're going to figure out delta V. That's going to be kind of the first step for a lot of these. Either the first step or the last step is going to be dealing with that delta V equation. So delta V equals V final minus V initial. Well, here are our velocities right here. So the roller coaster started at the top, so that's going to be V initial. It ends at the bottom, that's going to be V final. So V final is 25 meters per second, V initial is 10 meters per second. 25 minus 10 equals 15 meters per second. Okay, and then it says, if the roller coaster reaches the bottom of the hill in 3 seconds, how fast is it accelerating? So that's our question. So that's going to be where we put the question mark. And then the time is 3 seconds. Okay, so now we know delta V and we know T, and we're going to solve for A. Cover up A, we get A equals delta V over T. So A equals 15 divided by 3. A is going to equal 5 meters per second squared. Another way to say this is 5 meters per second. So they mean the same thing. You can write it either way. You'll kind of see me go back and forth between these two throughout today's lesson. A swimmer was losing her race, so she accelerated at 3 meters per second squared. Her speed increased from 1.5 meters per second to 1.8 meters per second as she accelerated. How much time did this acceleration take? So again, we're going to start off with this equation, delta V equals V final minus V initial. She started off going 1.5 meters per second. She ended going 1.8 meters per second. So 1.8 meters per second minus 1.5 meters per second. And that's going to give us 0.3 meters per second. All right, this acceleration was 3 meters per second squared. So we're going to add that in right here, 3 meters per second, right? That means the same thing as 3 meters per second squared. So I changed how it's written, but it means the same thing. If you prefer to write it this way up here, that's fine. So then the time, how much time did this acceleration take? Well, that's our unknown, so we're going to put a question mark there. We're going to cover up time in the formula. Time equals delta V over A. Time equals 0.3 divided by 3. Our delta V is 0.3. Our acceleration is 3 meters per second. 0.3 divided by 3 equals 0.1 seconds. So that's our time. Okay, last example. Mila is driving at 24 meters per second. She decides to race a friend, so she accelerates at 3 meters per second squared in 9 seconds. Should say for 9 seconds. What is her velocity at the end of this acceleration? Well, we're going to start off with this equation again. Delta V equals V final minus V initial. We know what her initial velocity is. That's 24 meters per second. We have no idea what her final velocity is, right? That's what the question's asking. So we really aren't going to be able to figure out what delta V is at the start of this question. We're going to deal with that at the end. To begin with, though, we do know what her acceleration is. That's 3 meters per second squared. So A equals 3 meters per second. We also know that she accelerated for 9 seconds, so that's going to be the time. Oh, whoops, I didn't realize I put that in there as 3 to begin with. Whoops, so it should be 3 here, not 9. Okay, all right, so then we're going to cover up delta V. We're left with delta V equals A times T. Because A and T are what's left, and they're on bottom. So then we're going to plug in for A and T. Delta V equals 3 times 9, which is going to be 27 meters per second. That's our change in velocity. Okay, so now we're going to use that to calculate what Mila's car's final velocity was. Right, that's the question. What is the final velocity of her car? Or what is the velocity at the end of the acceleration? So delta V equals V final minus V initial. And so delta V is 27 meters per second. I'm going to put that in for delta V, 27 meters per second equals V final minus V initial. Okay, but we don't know. Next we need to find V initial. Well, she started by driving at 24 meters per second. So that's going to go in right here. And so then to solve this equation, what we're going to have to do is do a little algebra and get this 24 over on the other side. How do we do that? Well, we need to add 24 to both sides of the equation. That will cancel these two 24s out, and we'll be left with 27 plus 24, which is 51 meters per second, and that's our final velocity. Okay, so no practice problems for today. There'll be some practice problems on this material tomorrow. Today you're just going to be taking notes.